Okay, we're recording. Hold on. I want to get my ugly mug up here in the corner in a second. All right. Finished grading. 99% of you have got your exams in. We had a few people that the flu bug caught, so we're awaiting them. They will take either a makeup or the test you did. I think it's probably best if they take a makeup. Of course, we're really good. In fact, I got an email from one of, and I'll talk more about this tomorrow. I just wanted to get us started on chapter 4, which is Newton's laws of motion. And I apologize because I plus slides, and I don't know if the OpenStax book that I sent you, I don't think it matters. I think if you watch these videos and 5% of all you need to do. The other 10% is coming to class. The other 10% is working on the problem, so we're up to 85. And about 15% is looking at what they have to say. The key is to look at their worked out problems, okay? And then go back and read the problem and see if you can do it yourself without copying it, without looking at it and just writing the formulas down, because now we're getting into, we're only adding static friction, we're only adding to what you already have, essentially. That's all we're doing is adding 3 more. Hey, I hit 10,000 steps. Anyway, focus, squirrel, is we're adding 3 more equations, okay? And I wanted to get you the basics. I'm going to do another probably longer video for you on Friday. And I might have to go babysit my granddaughter. Horrible thing tomorrow after class. I'll have to rush off to go sit with her. She's all well, but she can't go back to daycare until she's like no drugs for 24 hours or something like that. So her little 7-month-old body got racked pretty hard. Anyway, they're little disease bags anyway. Yeah, I mean, I go by a daycare and I'm like, man, I need a mask. So I'm going to at least get you started here on this, and I've already, so you can work on, you have no skills whatsoever to start that yet. you can look at it, and I have to be very, very careful now. I have found out that I'm learning too, that some of the problems that I didn't read fun. Oh yeah, we can do that. You know, they turned out to be hard, and I apologize for that. So, not really. Don't know, but you know, that was unfortunate, I guess, that kind of happened because they were good problems. You have a new homework assignment. It's due a week from tomorrow, and we're going to break chapter 4 down into 2 pieces. But I think for the most part, if we keep it super basic, that's one of the things is they try and make it so damn hard. By the time you get done, it's like, there's too much to that, and then this, that, and this. No, we're going to keep it forces. Newton's law, F equals ma, force equals mass. Let's talk about it. Let's get my mug off here, and we'll go through the first couple laws here. Okay, so here we are. Newton's law. All right, a force is a push or a pull. Okay, contact forces arise from physical contact. You actually push on, you touch it, or something is hooked up to something and pulling it, or something like that, or yeah, just. There's accidents that do not require contact and include gravity and electrical forces. Another action at a distance force is this past 4 or 5 days has been glorious running at 5:30 in the morning when I go for my little, 12 minute per mile jogging about 3 or 4 miles each morning. And I got my beautiful moon keeping me company while I'm running. There's been a few cloudy days, but like today is about a half moon, but there wasn't a cloud. It was sparkling, crisp, cold outside, and there's my little half moon. That is a force at a distance. That's that gravitational force that's keeping that moon from keeping on going, just flying towards the sun. But the Earth is pulling on it. It wants to keep going straight, but the Earth keeps pulling on it and tugging it closer to us. And it's actually getting further away in its orbit. Back in the dinosaur days, the moon was huge. It was like, when old T-Rex looked at the moon, he was like, whoa, man, that's a big-ass moon. Anyway, So, all right, arrows are used to represent forces. They're vectors, all right, and they're proportional to the force. Mass. All right, here's the big idea. Here's a big idea, and I'll stop here and record this a little bit. Mass is a measure of how much stuff something is. Mass is not weight. Okay? Mass is how much stuff there is in something. It is the kilogram. You are 75 kilograms on Earth. You are 75 kilograms on Mars. You are 75 kilograms on the Moon. You are 75 kilograms if you get to Pluto. Your mass does not change. You start hurtling close to the speed of light, your mass will go to infinity, and there's not enough energy in the universe to help you do that, but maybe dark matter can help. We don't know. But for the most part, until we get to relativity, our mass does not change. Okay? Weight, on the other hand, is a whole different ballgame because weight is actually the gravitational forces that are pulling on us, whether they're from the moon or the sun or the earth. That determines our weight. It's the force times gravity. The mass times gravity gives us the weight. Okay? All right. So Newton's first law, and we'll start with Newton's first law on the next slide, on the next whatever the hell these are. Oh, here we go.